So this kind of remind us where we were. So we're talking about a few things. Basically, the point of this is an area called stoichiometry, where you're trying to relate, if I use this much of a reactance, how much of a product will I go out? And the first case we did was if we just put in one reactant, then you could predict, okay, well that one reactant will give me how much product. But then I said, well, what if you know the amounts of, let's say, two different reactants? Well, you can figure out how much product reactant A will give me and how much product reactant B could give me. But one of those is going to be what's called the limiting reactant. Well, so the one that gives you the least amount of product, well, that reactant is going to run out first. That's going to limit how much you can make. The other reactant we said will give you more than enough, and that would be the excess. So that was the whole thing with the limiting reactants. So I said, okay, how about this thing called percent yield? Well, the one you calculate how much you could make theoretically if everything went perfectly, that's called the theoretical yield. That goes on the bottom. And then when you actually run the reaction in the lab and you do it, well, you may not actually get out that much. You may get out a little bit less, so that's called the actual yield. And this gives you then what's called the percent yield. So it's the amount you actually got divided by the amount you calculated you should have got if everything went flawlessly times 100. So then we looked at calculating percent yield here. So, did we do all of 16?
No.
Okay. Okay, so let's look at an example here. So we're going to do the whole thing. We're going to balance the equation. We're going to find the limiting reactant, how much you should have made, and then they're going to tell you how much we actually made, then you can find the percent yield. So, first step is we're going to balance the equation. So, I'll just give you a couple seconds there to figure out how to balance that. You can talk it over if you need to. So just try it out and then compare your answer there with somebody. So balance your carbons, balance your hydrogens. Which element out of those three do you want to balance last, by the way? Remember, I gave you some little tips on balancing? Or does it not matter? It does matter, but... Yes, you want to balance the oxygens last. Why? Because the oxygen appears, yes, in two different places, right? The oxygen appears in two places on the same side. So that means balance this one last. So balance the carbons and hydrogens first, and balance the oxygens last. Else you will go crazy. Okay, so try it out, and then compare with your neighbor there, see what you think. See you get it? Okay, talk it over with somebody, see what you got. What'd you get for the, you know... Okay, what's going on here? Knock me off the line? No? Okay, so what'd you get when you balanced it? 1534. Anybody else?
That's good.
Okay, sorry, my computer is really pissing me off here. Yeah, 1534. So 3 carbons on the left means you need to put a 3 here. 8 hydrogens and 2, so to make that 8, you put a 4 there, 4 times 2. And that gives you a 3 times 2, 6, plus 4 times 1, 4 is 10. So to make this 10, you put a 5 there. So 1, 5, 3, 4. Okay, so we balanced it. So what's next? So now it says, let's say you have 5 grams of this and 20 grams of this. How much water could you make if everything went perfectly? So again, it gives 2 reactants. So we're going to do that twice. I'm going to turn the 5 grams into water. I'm going to turn the 20 grams into water. And out of the 2 possible answers, which one will you pick? The smallest one. Yes, the least, right? Whichever one gives you the least. So try it out. So take 5 grams of 5.0 grams of propane. How much water could you make? Do the same thing for oxygen. How much water could you make?
How much do you miss?
So start with 5.00 grams C3H8, and then you should all know what to do first. You got the mass of something, there's only one thing you can do. So what's the first thing you're going to do? Some of you are molar mass, right? You're going to turn that mass of C3H8 into moles of C3H8. So add up 3 carbons, 8 hydrogens. You should see a lot of periodic tables out. And then you'll be in moles of propane, but you want to be in moles of hydrogen. So keep going there, help each other out. How do you relate propane to water?
Mole to mole.
Mole to mole ratio, which is, what is it?
1 to 4.
Yeah, for every 1 mole of C3H8, you make 4 moles of water, right? Then you'll have moles of water, but you want the amount, the mass. So find the grams of water. So moles to grams. And this is pretty much sunk in by now. You've had 5 days to do the homework.
So the smaller one is the theoretical yield?
Yes.
And
Water can't be 20, by the way. Oxygen's 16 and hydrogen's 1. Should be like 18.02.
so the one that uses the smaller one, that's the limiting reactant?
Yes, right. That's the reactant. It's
And
going
the,
to
what is that other one called?
the excess.
Excess.
Because you have more than enough of this, because you can go past that point.
Yeah.
I have a question. So that's the thing that I was getting confused in the moment. Because since it's water, it's H2O.
Yes.
When I add 16 plus 2.02.
18, yes. It's not 2 times 2.02. Okay, what'd you get for the theoretical mass of water from propane for the first one? C3H8 can make how much water?
8.17.
8.17 grams. Okay. Keep going. Okay, there's the first one. Talk it over if you haven't yet. What did you get for the oxygen? How much water would the 20 grams of oxygen give you? So talk it over with somebody. Help each other out.
The formula for percent yield is actual over theoretical.
Huh? No, because you're trying to cancel the O2. So the O2 that I'm yeah. And then you cancel out the 1 mole H2, and then you give him his I know, but then you go to him this when it comes to and then
What's the relationship between oxygen and water?
oh, it's this one.
5 to 4.
Yeah. No, I'm doing it. So for the actual yield, would it go that one on the top, and then the theoretical yield would go on the bottom, and then I'll times it times 100?
The theoretical one's the one you just found on part B.
Theoretical, part B, okay, so
So it's the smallest one. You have 2 possible ones. How much theoretically you should make this amount?
Mm-hmm.
That's your theoretical.
Mm-hmm.
The actual is the one they give you. How about if you actually only made 6.21?
Oh, okay.
Yes. Start with 20 grams.
Yes.
You get 1 mole.
Yeah, you're right. That's exactly right.
Okay.
Good job. Okay, looks like most of you got the other one. Okay, well, I see a bunch of people have like 9.01. Is that what you got? Okay, good. Well, let's just work it real quick. So do the same thing, but now do it for the oxygen. 20.00 grams of oxygen. Got mass of oxygen. All you can do with mass is molar mass. So add up 2 oxygens. So 1 mole of oxygen is 32.00 grams. And now I don't want oxygen though. I want to know water, I'm sorry. And that for every 5 moles of oxygen, we make 4 moles of water. So use that mole to mole ratio. 5 moles O2 on the bottom. 4 moles H2O on the top. And then we want mass, so turn moles into mass. So molar mass again, 18.02 grams is a mole of water. And 9.01 grams. So we had 2 possible answers. There's enough propane to make 8.17 grams. There's enough oxygen to make 9.01 grams. How much will you actually make? 8.17, right? So that means propane was the limiting reactant, right? Because it limited us to only 8.17. And what do we call the oxygen? Yeah, that's the excess reactant, right? Okay, so that's our theoretical. Our theoretical yield, the amount you would make if everything went perfectly in the lab or the factory or whatever, would be 8.17 grams. However, they tell you it didn't go perfectly, and they only made 6.21 grams. So what is the percent yield? Oh, well, take the actual 6.21 grams over the theoretical, the amount you just calculated you should have made, 8.17, and multiply that by 100. And what is that?
76.0.
76.0%. Sounds good. 3-6 phase. Yeah, good. Okay, questions? Some of you got that down, so that's good. Some of you a little bit struggling, but yeah.
Why 8.17?
Well, you have to pick one of the two from Part B, because so in Part B it said, okay, the 5 grams of propane allows you to make 8.17 grams of water. The 20 grams of oxygen allows you to make 9.01 grams of water. Well, the propane runs out once we get to 8.17. There's enough oxygen then, of course, to keep going all the way up to 9.01, but we can't because the propane runs out. So we're limited to only making whatever the smaller amount is, the 8.17. So you always pick the smaller of the two possibilities, or the three possibilities.
Will the actual yield always be smaller than the theoretical yield?
It doesn't matter.
Like most, like 99% of the
I
time?
mean, it should be. Okay, let me say, theoretically, it should be always smaller because it's impossible for you to make more than you can. However, though, I will say, though, sometimes, though, like in the lab, let's say you're supposed to make 5 grams of something and you filter it with a bunch of water and you don't quite get it dry, and actually wind up weighing like 5.5. So you're like, wait, my yield is 110%. How's that possible? How did I actually make something out of nothing? Well, so I'm saying, theoretically, it has to be 100% or less. But there are other ways, like I said, if you're actually way more, just like contamination and things like that.
Okay.
But ideally, it should always be 100 or less, of course. So, okay, well, last couple little topics here. We're going to discuss a little bit of energy. And we'll wrap it up, do a little naming practice, and then we'll do a little science fair groups and get out of here. So, when things want to react, molecules swirling around a beaker or in the air or whatever, you got to have a few things for those molecules to actually react. First is they have to actually come into contact with each other. They have to actually collide in order for them to react. They can't just react from across the room, right? It's like making babies. You can't have babies across the room from each other. You have to collide. So that's the first thing. They have to come into contact with each other. The second thing they have to do is they have to collide with the right orientation. They can't just connect random different ways. They have to connect the right way. It's like you have Legos, right? So Legos will only connect if they go a certain way, right? So you can't just turn them sideways or whatever, top to top, bottom to bottom. You have to go the right way. So they have to collide in the right way. And the third piece of the puzzle when they're colliding is they can't just gently bounce off of each other, but they have to have enough energy to actually cause that reaction to occur. So when reactions are occurring, think about what's happening. Some of those bonds in the reactants are breaking apart, and then some of the bonds then are reforming to make those products. So you have to have enough energy when they collide to actually break those bonds apart in the first place. If you just gently tap them together, well, they won't snap the bonds and free them up to react. So 3 things. They got to collide. They got to collide the right way, and they got to collide with enough energy to actually drive the reaction. So that amount of energy that you need to drive that reaction is something called the activation energy, and actually it's a combination of various things of the collisions and the orientation too. But we'll come back in 111. I'll teach you about that. But in general, yeah. So they need enough energy to actually start the reaction. So 3 things. So that's called the activation energy, and you will see that abbreviated oftentimes as capital E with a little a subscript down here. That's the activation energy. So that's the amount of energy we need to snap those bonds in the reactants and get the reaction going. Okay? So, if you don't hit them hard enough, well, they just, bounce off each other and nothing happens. There's no reaction occurring. Okay. So all the time then, in a beaker, in the air, whatever, there are millions of collisions going on, and maybe it's 1 in 1,000 or 1 in 10,000 actually have the correct orientation and enough energy to actually cause the reaction. Which is why generally, when a reaction needs to go faster, you want to do a couple of things. You want to make them collide more often, so you have a better chance of them getting the right orientation, if they're just smacking together more often, and you want them to hit each other harder and faster. And that's where we'll see temperature comes in, because as things get hotter, we know they move faster and faster, right? So that's a couple of ways we can speed it up, but we'll come back to that a little later. Okay, so if I was going to draw a little picture of how this might look, there's two possible scenarios. One is the one on the left, where the amount of energy that is stored up in the bonds of the reactants is higher than the amount of energy that's all stored up in the bonds of the products. So to go from here to here, you still have to get over that hump where you have to actually break those bonds apart, and that takes an amount of energy. So you got to get up over this hump, and then it's all just downhill, and everything goes to products. Or you can have a case where the amount of energy initially present in the reactants is lower than the amount of energy in the products. But it's the same deal. There's going to be a hump you have to get it up to, and then it's downhill, and it's easy to get to products. Okay? Okay? Like if you're golfing, let's say, or if you're golfing or you're putting, let's say, you have a little hill, right? So you want to hit it hard enough that it not just here and rolls back down, right? It's got to get enough energy to get up, and then it's downhill after that, right? Right? Or a roller coaster or something. So the amount of energy to get over that hump, whatever that hump is, that's the EA. That's the activation energy. So if the energy contained in your reactants is greater than the energy in your products, well, you have to lose energy between here and here. And when you lose energy or lose heat, that's called exothermic. So exothermic means heat is released, heat is lost. And the opposite of that is if the energy of the products at the end is greater, well, then it must have picked up some energy. It must have absorbed some energy. That's called endothermic. Heat is absorbed. So exo, heat is exiting, exo. And endo, it's being absorbed. It's going into the reaction, is a way to think about it. Exiting, exo, going into, endo. So okay, so now we can actually measure that heat difference. There's entire books full of tables for all kinds of reactions where they've run thousands of reactions they've measured. Okay, so how much heat was there? It was either absorbed or that was released when these reactions were done. And that is typically called the enthalpy of the reaction. So I'm trying to pause. I'm killing time here. You're scribbling. Okay, go find that PowerPoint later. Finish it up. That's called the enthalpy of the reaction. We call this delta H. The delta H. So the amount of energy, the heat of the reaction here, the difference in the products and the reactants, that's the delta H. That's the products minus the reactants.
The word for that is enthalpy?
Enthalpy. I'll show you that here in a second, actually. But I'll get there in a second. But yeah, it's called enthalpy. I'll just write it on here. Yeah, that's probably a new word to you. The enthalpy. So products is greater than reactants, it's going to be a positive number. If products is less than reactants, it's going to be a negative number. So to show you that. So for example, let's say we take carbon plus oxygen, we combine those and we make carbon dioxide. Well, that is a case where it is a negative 394. So energy was lost. So the energy of the carbon and the oxygen was higher than the energy of the carbon dioxide. So it had to lose some energy. How much did it lose? It lost 394. So notice then the heat or the enthalpy has a negative sign because heat was lost. It lost heat, negative, right? Heat went down. So that reaction then would feel hot to the touch if you were to run it. It would feel warm because you feel the heat giving off. You probably felt exothermic reactions before, probably, you know. So like those hot packs and you buy them, you crush them and you rub them together and they get really, really hot or something. That's That's an exothermic reaction, right? It's giving off heat, it's releasing heat, has a negative delta H. Well, the opposite is, let's say, endothermic. So let's say nitrogen and oxygen combine to make nitrogen monoxide. Well, that has a positive number, right? That's a positive 180. So that means that one has to gain 180 kilojoules from where it started to where it ended. So that's called endothermic. And you also see that like with ice packs, right? You have ice packs, you crush them, shake them up, and they get really cold, right? Right. You had those before. So those are endothermic reactions, like positive delta H, a positive enthalpy. Okay, well, like I said, there's tables full of these reactions where they have measured it, oh, it's positive or negative or whatever it is, and what the value is. And notice we're using our old units, kilojoules, because again, this is heat, right? Way to measure heat, kilojoules. So let's just look at one. So here is the enthalpy, or the amount of heat, for the one we just discussed, the propane combustion, right? Remember 1 to 5 to 3 to 4 we just did? So for every 1 mole of propane that you burn, it releases negative 2,044 kilojoules of heat. So this amount of heat is for this reaction as written. So that means it's 2,044 kilojoules for every 1 mole of propane. Or it's 2,044 kilojoules for every 5 moles of oxygen, or 3 moles of carbon dioxide, or 4 moles of water. So that means, let's say then that I burned 5 moles of propane, well, I would get out 5 times that amount of heat. Does that make sense? If I burn 10 moles, it would be 10 times the amount of heat, right? Because that is per 1 mole, or that is per 5 moles of oxygen. Okay, so I could write a couple different ways there. So this is per whatever you're looking at. This per 1 propane, or this per 5 oxygens, or this per 3, or this per 4 moles of water. Are you with me? So we could write all kinds of different little conversion factors to turn moles into heat. So let me show you a couple. We'll do a couple examples, and then we'll be done. Okay, so let's look at a couple examples here I have up here for you. Let's just do one. Let's do the reaction. Let's say I wanted to burn 13.2 kilograms of propane. Okay, so here's an important thing, right? So you want to make sure, okay, how much heat will this produce, right? So you're an engineer or something, and you want to know, okay, how much heat will this reaction give off? Is it going to be too hot for my stove, for my rocket? Is it going to melt the whole thing or not? So you want to know, okay, calculate how much heat will this give off. So let's just start with what we know. We know 13.2 kilograms of propane. Now I know it gives off 2,044 kilojoules per every 1 mole of propane, but I'm in kilograms of propane. So what could I do to get me from kilograms to moles? First, let's turn those kilograms into grams. So kilos, 10 to the third. So 1 kilogram is 10 to the third grams. And now I'm in grams of propane. So what would I do? Molar mass. So we'll add up 3 carbons, 8 hydrogens. It'll be 44.11, right?
Yeah.
There's a mole of propane. Okay. Now I'm in moles of propane, but I want to be in kilojoules. So that's where the enthalpy, the heat of the reaction, comes in. Because that tells me there's negative 2,044 kilojoules per every 1 mole of propane, right? Now again, it's not always just 1, it's whatever that coefficient is on the thing you're looking at, right? So if the reaction had been for oxygens, I had to put 5 on the bottom, right? If it was carbon dioxide, I had to put 3 on the bottom, right? So it's not always 1. It's not like molar mass where it's always 1. It's whatever that coefficient is. Okay, so punch that in your calculators. Let's see what you get. You're going to get some negative number because heat is being lost, being evolved. Good. Oops. Okay, I got negative 6.12 times 10 to the 5th. Anybody else?
Yep, that's
Okay, good. No? Not getting that? 13.2 times exponent 3 divided by 44.11 times negative 2044. There you go. Okay, good. Okay. Let's try a little rocket science. Literally. Let's discuss the Apollo moon missions. So in the Apollo landing modules, the fuel they used was hydrazine, and they reacted that with an oxidizer, dinitrogen tetraoxide. So you might want to know, okay, so how much heat will be given off by the landing module when I burn a certain amount of fuel? Again, you're concerned with the temperature of the landing module or whatever, right? It's not getting too hot. So it says if I burn 273.9 grams of hydrazine, how much heat will I give off? Well, I know there's 1,049 kilojoules of heat given off for every 2 moles of hydrazine, right? Yes? Okay, thank you. So let's try this out. So 273.9 grams of hydrazine. What would I do first? Molar mass. I got mass. All you can do is moles. So let's try molar mass. So add up 2 N's, 4 H's, 32.06, I think. I've just done a lot of N's and H's and C's. I know this pretty quick. Now I'm in moles of hydrazine. So what would I do next to find the heat? What would I do?
2 moles of
Not mole to mole.
heat, 2 moles.
Yeah, kilojoules. So I would put what on top, what on bottom? Just walk me through it here. Put what on bottom? How many moles?
2.
For every 2 moles of N2H4. And on top? Negative 1,049 kilojoules, right? So everybody sees where that came from, right? Came from this 2 right here. Okay. Looks like 4 sig figs, 4 sig figs, 4 sig figs, exact. So it's going to be 4 sig figs. So see what you get. Okay, what'd you get? Negative something with 4 sig figs.
Negative 4,408.
Negative 4,481. Anybody else?
I got that.
Okay, so there you go. So now you know how much heat was given off. And then if you want to know the temperature change, we could use that old equation. Remember, Q equals MC delta T, specific heat thing. We could put in specific heat of, let's say, the metal the module is made out of. You can figure out, okay, so how hot's that metal going to get? Is it going to fry the astronauts alive? We can figure that up using that kind of thing. So, okay, last one. Have any veterans in here? I know we have people actually serving. I mean. So here's your favorite thing in the world. We're going to look at MREs. So MREs use a exothermic reaction oftentimes. One of the ways they heat them up is you have this little pouch your food comes in, you pull the food out, and then it has in the bottom some magnesium, you pour some water in there, and it gets really hot. That's an exothermic reaction. You put your food back in the bag and it heats the food up. So here's one of the reactions used in MREs. So how many kilojoules of heat would I give off if I dumped in 25 grams of water into my lovely MRE bag? How many kilojoules would I give off? So figure it out. Okay, any questions on that? Okay, well,